Naturally occurring uranium contains mostly uranium-238 and needs to be enriched to increase the amount of uranium-235. The level of uranium-235 isotope in uranium ore is 0.72%. It is 3.5% in nuclear plant fuel rods and 90% in nuclear bombs. The ore is first made into yellow cake. Fluorine is then added to create gaseous uranium hexafluoride. Uranium hexafluoride can be enriched by diffusion. The gas is pumped through a high-pressure feed stream into a low-pressure chamber fitted with a porous membrane. As uranium-235 is smaller than uranium-238, it passes through the membrane faster, making uranium-235 enrichment possible. Most enrichment plants today use centrifuges. As the centrifuge spins, the heavier uranium-238 is forced towards the walls, while the uranium-235 stays in the center. The gas can either be enriched to 3.5%, which is suitable for fuel rods, or enriched further to 90% to make nuclear bomb fuel. The Israeli PM on Sunday urged the US to ban Iran from enriching uranium beyond 3.5%.
In this video, we're going to see how the different isotopes of uranium in uranium hexafluoride can be separated using diffusion or centrifugation, causing fuel enrichment. So going back to the problem is naturally, if we get a sample of uranium, about 99.2% of it is a stable isotope called uranium-238. We really need the uranium-235 to actually have chain reactions, because it can be bombarded by a neutron and it can split into two new nuclei. This is fission. Fission is breaking. And in that process, it emits more neutrons, which can then bombard other uranium-235s, which can then split through fission and produce more neutrons, which hit more uranium-235, and we get what we call a nuclear reaction. So the problem is, if we don't have many uranium-235s, these neutrons that are shooting out may hit a uranium-238, and then nothing will happen. And when nothing happens, then you can't generate any electricity, or you can't use it in a bomb. So the idea is to get more of these uranium-235s around so that when these neutrons come out, they do have another one to collide with. So we find here that reactor grade, like in a nuclear power plant, we need to increase it from 0.72% to about 3 to 4% to have enough uranium-235s statistically to get bombarded with those neutrons and continue the chain reaction. And if we want to go to the weapons grade, we need 90% enrichment, in which case you get a lot of chain reactions, a lot of this happening, and every time this happens, there's a lot of energy released. So how do we try and get more uranium-235s? Well, there are two ways that we do this. And before we can really get into it, we have to understand the difference between what we call diffusion and effusion. So diffusion is illustrated here as the idea if you have particles in a sort of higher pressure or higher concentration area versus a low concentration area, and they're separated. If you remove that partition, these particles will diffuse and equalize the concentration around. Now, effusion is very much the same way. If you have a hole, they're going to try and go through and equalize, but the difference here is that the effusion is through a hole, and so it's actually restricted in its movement. And so what they're actually able to do is sort of use this measurement of how fast things effuse through the hole, which is usually based on their size, to help us sort of understand how fast things diffuse when there's no sort of barrier there. So let's look at what happens with, for example, uranium. So if here we have a side with uranium-238s, which are the bigger ones because they have a larger nucleus, and uranium-235s, and we want more uranium-235s. So what we do is we react the uranium with fluorine, and that creates gaseous uranium compound. So it's gaseous, so it will therefore undergo effusion and diffusion. So what will happen is if we open up this hole here, the smaller particles will preferentially end up going through because of their size and the fact that they're moving a little bit faster, because when they're at the same temperature, a smaller particle will move faster than a larger particle. Much like, if you had two football players, one who's really small and one who's very large, even if they have the same energy, that small football player can get running faster, but that bigger one is going to be a bit slower because it has more mass to move. So after a while, you'll actually see that the ratio has sort of become enriched. We have more uranium-235s, in other words, 3 to every 2 here, whereas here we had 1, 2, 3, 4, 5, 6, 6 to 6, so that was a 1-to-1 ratio. Now we have a 3-to-2 ratio. So we could take this off, and then we could actually put it back, that sample back again, and have it fuse again, and just have it continue until we get the ratio that we want. So we can see that one side gets enriched with these smaller molecules, and the bigger ones kind of get left behind and enrich on that side. So that's how we can get a higher percentage of uranium. Now the second way is through using a centrifuge, and here we're representing it very simply with a test tube. So when you do a centrifuge, that's essentially something that is causing a spinning motion. And this kind of imagine yourself like on one of the amusement park rides where it spins you around. Well, if you are being spun around, like on a merry-go-round, what will happen is something that has more mass will end up sinking further towards the end, and something that's lighter will end up being more towards the center. So you can see they started here in the same position, but as soon as we start spinning them, the heavier one gets thrown to the back and the lighter one up to the front. So we can then try and take the uranium-235 from the front part of the centrifuge and then use that for our enrichment. Or we could just simply extract the ones that end up on the end and be left with those. So those are two different ways that we can enrich uranium hexafluoride.